Okay, so this is light lesson 4. We are going to talk about light interference. So hopefully this pattern that's on the screen looks familiar to you. This is, if you recall, a wave interference pattern. So in our waves unit, we looked at what happened when two-dimensional waves interacted, so water waves in a ripple tank. As long as your two sources are in phase, so they're in sync, and they are at a constant distance, so the constant distance between source 1 and source 2, and as long as frequency doesn't change, you will get this interference pattern. Okay, it's stationary. So if you remember, destructive interference is shown by these shaded gray lines, or the nodal lines. So those are where your crests and troughs meet, high point and low point of the wave. And then you've got constructive interference happening, where the dots are, when you have either crests and crests meeting, or troughs and troughs. So they get twice as big, twice as high, or twice as small. So light is a wave, so in theory, if you have waves creating an interference pattern in water, such as this, you should also see light creating some kind of interference pattern. So if light has wave properties, then two sources of light waves should produce the same result to that of waves interfering in a ripple tank. So in Newton's time, many scientists attempted to observe the interference of light. And to do this, they would place two sources side by side. The light would fall on a screen, and when examined, there was no interference observed, which shouldn't have happened. So it turns out that there were two problems with the way they did this. At the time, problem number one is that they didn't know the wavelength of light was extremely small. So we know that light travels very fast, but it also has a very small wavelength. So when you have waves in a ripple tank vibrating at a high frequency, the wavelength is small, the distance between the adjacent nodal lines is small. So early experiments produced results with nodal lines that were so close together that you couldn't actually observe them. So there was an interference pattern, it just wasn't visible. It was not distinguishable by the human eye. Okay, they didn't know this, but we know it now. And problem number two was that in a ripple tank, you have to have those two sources being in sync, but if you're using two separate light sources, the light is emitted randomly by each source, which means that they are out of sync. Or we could say not in phase. Okay, they're not emitting their light together, so therefore sources are not in sync. We need to have the sources in phase to observe this interference pattern. So this problem was solved by a gentleman by the name of Thomas Young. So he performed a number of experiments, and he actually used a single light source. So that would be here. This is your light source. There was only one of them. But what he did was he directed that light through two slits, or two pinholes, that were very close together. And the light was diffracted through each pinhole, so the waves moved through the gap, through the hole. And by having these two slits, they both acted like their own source of light. So we created two different places the light was coming from, or two sources, but they were both produced by one single bulb. Okay, and this was super, super key. So on the screen, what we observed was constructive interference and destructive interference. Where constructive interference happened, they were bright spots. Okay, so this was a bright band. Then we got a dark band where destructive interference occurred. Then we got more constructive, which was bright, dark, bright. So you could actually see the alternating bands. So since the sources were close together, the spacing between the nodal lines was great enough that the pattern could be seen. So because the light came from the same source, which was your single light source, the two beams were always in phase because they were coming from the same source. So let's highlight that. The two interfering beams were always in phase. And then you could have a fixed interference pattern being created. So Young actually solved both of the original problems by creating those super close together slits. The distance between the sources was small enough that you could see the pattern. And the very important thing also is the two sources were in phase because they really came from the same single light bulb. Okay? And this was huge evidence for the wave theory of light, because light acting like a wave produces an interference pattern. They observed the interference pattern and they were like, aha, light must be a wave. So let's look a little bit closer at the math. So if we look at these diagrams, they show the light passing through two of the sources. So in diagram 1, both waves reach the center of the screen. They're in phase. They're traveling the same distance. Okay, distance from source 1, remember it's really coming from the same light bulb. The distance from source 1 to the screen and source 2 from the screen is the same, so the waves are completely in phase. They travel the same distance in the same time, so they both reach the screen at the same point in their trough, crest pattern. So we get a bright spot on the screen. Okay. In diagram 2, we have those waves traveling slightly different distances. Okay, so from source 2 to the screen, they're traveling a little bit further. They actually travel an extra half of a wavelength to reach the screen. So if you look, it reaches about halfway through its cycle between crest and trough. So we actually end up with them canceling each other out. So the crest of one wave meets the trough of the other. So crest meets trough, destructive interference occurs, and we get a dark screen at that point. In the third diagram, we're moving even further from the center of the screen, so we've reached a point where the path length difference is one wavelength, so they're back in phase. So from source 2, this wave has to travel a full wavelength further, but they both reach the screen at the same point in their cycle. So we have a crest meeting a crest, and this is because those waves from source 2 are a full wavelength behind the waves from source 1, so we have constructive interference occurring once again. Okay? So constructive interference is when the path length difference is a whole wavelength. So between the two sources, they're out of phase by a full wavelength. Whether that's 1, 2, 3 wavelengths, they're out of sync by a full wavelength, so they meet up at the same point. Crest and crest, trough and trough, we get a bright spot. Destructive interference occurs when the path length difference is half a wavelength, or they're out of phase by n/2 times the wavelength. So whether that's a half a wavelength, 1.5 wavelengths, 2.5 wavelengths, they meet at crest and trough, which means they cancel out and we get a dark spot. Okay, so this is bright, and this would be a dark spot. Okay, so we can create an equation representing this relationship. Here it is, this bad boy right there. Delta x represents the separation of the nodal lines. So that's the separation of the bright and the dark spots that you actually see over on your screen. Lambda represents the wavelength of the light. So depending on what kind of light or what color light, there are different wavelengths. D represents the distance between the slits. With a slit separation. And then L represents the distance from slits to the screen. Okay, so if we look up here, this first diagram actually shows it. L is the distance from the sources to the screen. Make that bigger. Then we've got the distance between the actual slits. And then over on this side, we would have the separation of the band. So between this band and this band, this band, and this band, that would be represented by delta x. Now the most common mistake is people getting delta x and d mixed up. They mix up which is the separation of nodal lines, which is the separation of the slits. So I like to think of the x as being like cross. So I think of the bands of light, so I think of the bright and the dark. But that's just what works in my head. I don't know if it'll work in your head. Right. Look at a couple of examples. So example 1, we have two adjacent nodal lines that are 9.7 centimeters apart. The distance between the slits is 34 micrometers, and the distance from slits to screen is 5.2 meters. And our task is to find the wavelength of the light. So 9.7 centimeters apart, the adjacent nodal lines, that will be our x, delta x, 9.7 centimeters. Distance between slits, 34 micrometers. That will be d. And last but not least, distance from slits to screen is 5.2. That will be L. We're looking for lambda. Now, we have to be really careful when we do problems like this because our units need to match. And if you look, centimeters, micrometers, meters, none of them match. So we need to convert them all into the same unit before we actually do the calculation. So what I like to do, what I suggest, is that you convert all of the values to meters. It's easiest to go back and forth between the standard unit and then whatever you have. So I'm going to pull out this handy dandy little chart. It's a little small, but you should have one as well. We're going to convert centimeters to meters. So from the standard, that's just 10 to the power of 0. Centimeters are represented by 10 to the power of negative 2. Now, instead of moving my decimal off the bat, I'm just going to multiply this by 10 to the power of negative 2, and that will represent centimeters. So 9.7 centimeters is really 9.7 times 10 to the power of negative 2 meters. Okay, and if you want to see what this actually looks like in your calculator, 9.7 times 10 to the power of negative 2 is 0.097. So you can go ahead and write it as 0.097, or you can leave it like this to punch into your calculator later. Doesn't matter. Whatever you feel comfortable with. A different way you can punch in exponents is if you go, so let's go 9.7, and instead of going times 10 to the power, what you can do is use the EXP button. So the EXP button automatically puts in the times 10 to the power of whatever. So you just have to enter your exponent, which in this case is negative 2. So negative 2. And it also gives you 0.097. Okay, and now that's meters. So we've converted this into meters. Let's go to the next one. So 34 micrometers. Micrometers is 10 to the power of negative 6. So what we'll do is you could either move your decimal 6 times to get it to standard, or you can just go 34 times 10 to the power of negative 6. So 34 times 10 to the power of negative 6 meters. Okay? And if you prefer to write it out as a decimal when you're doing your work, we can write it as a decimal. So 34 exponent negative 6. You could also write it 0.00034. Oops. It's all what you're comfortable with when you're punching all of this into your calculator eventually. So once again, from 9.7, to get it from centimeters to meters, you can represent it as times 10 to the power of negative 2, because a centimeter is a power of 10 to the negative 2. Or you could just straight up move your decimal. So if your decimal's here, we move it twice to get to the standard. So 0.097. For micrometers, micrometers is a power of net 10 to the negative 6. So we multiply whatever number it is, 34, times 10 to the power of negative 6. Or, if you prefer the decimal moving method, we move our decimal 6 times to the left. 1, 2, 3, 4, 5, 6. So we end up with 0.12340, 34. Okay? Now we have all of our numbers in the same units, so we can go ahead and use our formula. Get this out of the way. So our formula is lambda is equal to delta x times d over L. This could also be written as delta x times d all over L. Doesn't matter, because really this is like delta x over 1. Delta x times d is delta xd. 1 times L is L. We don't have to rearrange our formula. It's already set up so that we can solve for lambda. So lambda equals delta x. I'm just going to write in the decimals, like so, times d, which is 0.00034, all over 5.2 meters. Okay, when punching this into your calculator, be careful how you're doing it. I like to punch in chunks. I'm a chunky puncher. So 0.097 times 0.1234. I hit equals, and then I divide by 5.2. Divide 5.2. We get, wow, that's a lot of zeros. If I'm counting correctly, it looks like 6. 1, 2, 3, 4, 5, 6. 6, 3, 4 meters. Okay? That's a really, really small number. So in this question, it doesn't ask us a particular unit in which we need to record our answer. But what we can do is kind of pick a unit that makes more sense. Because if you tell somebody the wavelength of light is 0.000000634 meters, that doesn't really mean much. So if we wanted to move the decimal to the end of this number, we would have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 times. If we moved our decimal 9 times from standard, we would end up with 10 to the power of 9. That would be nanometers. So we could actually express this as nanometers and have it make a little bit more sense for somebody who's looking at this. So if we move our decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 times, we are now in nanometers territory. And most wavelengths of light are expressed in nanometers or micrometers. Because the wavelength of light is so small, nanometers make the most sense. All right. So again, the tricky part of these questions is getting your values to be the same units. And then when you're actually inputting these values into the computer, making sure you don't make punching errors as you're putting them in. All right, so let's have a look at example number 2. Oh, I should say, if you wanted to leave your answer like this, that's fine. You could even put it into scientific notation if you wanted to, or you could convert it to nanometers. Sometimes the question will ask you specifically what units you need to answer in, so just watch for that. Okay, example number 2. If the wavelength of light is 540 nanometers, we're going to have to rearrange our equation, and the screen is 3 meters away, so that is our L, and the distance between adjacent nodal lines is 6. So adjacent nodal lines, those are your bright and dark spots, so that will be delta x. We're looking for D, right? So we're going to have to figure out how to get these all into the same unit. So let's do that. We're going from nanometers to meters. We're going from here to the standard. So we can take 540, multiply it by 10 to the power of negative 9. Or what we could do is, if you prefer to just move the decimal, we're going to move the decimal from the end 9 times. Okay, so we end up with 1, 2, 3, 4, 5, 6, 540 meters. Okay, you can do this or this. You do not have to do both, whatever you prefer. 3 meters, that's fine. We don't have to convert that at all. But 6 centimeters. So centimeters is times 10 to the negative 2. So we'll take whatever number we have, which is 6, and we just multiply it by 10 to the power of negative 2 to turn it into meters. Now you could also decide that you just want to move your decimal. So from 6, we would be moving it from here to there, going to the left, 2 units, 1, 2. Okay. Be 0.0600 meters. All right, now that we've established our actual numbers, we have to go ahead and figure out what version of the formula we're going to use. So lambda equals delta x times d over L. We're looking to get d by itself. Now, if you're someone who likes to rearrange the formula first before you plug in your numbers, we'll do that. So we got to get d by itself, which means we need to get L out of the denominator. Let's multiply both sides by L. Our L's will cancel out, and we are left with L times lambda equals delta x times d. Now we're still not done because we want to get d by itself, so we will go divide by delta x, divide by delta x. Delta x's cancel out, we're left with d equals L times lambda over x. All right, let's go ahead and put our numbers in. So d equals L, which is 3, times lambda. This time, I'll put in the scientific notation instead. Divide by delta x, so that's 6 times 10 to the negative 2. Now, when we go to punch this into the calculator, I'll try to get the whole calculator in here, but not in the glare. Again, I'm going to punch it in chunks. So 3 times, I like to put my exponents in brackets, you don't have to, 540 exponent, negative 9, close the bracket. Let's figure out what that equals. Now we still haven't dealt with the divide, so I'm going to hit divided by 6.00 exponent negative 2 equals, and we get 0.00027 meters. Right? Now we could leave it like this. You could put it into scientific notation from here. So I could put it into 2.7 times 10 to the power of negative 1, 2, 3, 4, 5. Right? It's a small number. We move the decimal 5 times, which means negative 5. You could also decide, hey, this is a really small number for meters. I want to use units that make sense. You could look and go, well, if we have to move the decimal about 5 or 6 times, we could maybe express it as millimeters, or we could express it as micrometers. It's up to you. For millimeters, we would move the decimal 3 times to the right. So we could say 1, 2, 3, 0.027 millimeters. That's still quite a small number. So maybe let's instead use micrometers. So we would have to move our decimal 6 times to the right. 1, 2, 3, 4, 5, 6. Oh, so we'd kind of have 27. So we could say 27 micrometers. That would also work. It's up to you, right? I'm going to go back, and from our original equation, there are some of you who may prefer to punch in your numbers before you isolate for the variable. So we're looking for D. So we would plug in all the numbers we know. 540 times 10 to the power of negative 9 is equal to delta x, which is 6, times 10 to the negative 2, times D, divide by 3 meters. From here, you would multiply both sides by 3. So you'd end up with D times 6 times 10 to the power of negative 2 equals, and then you could find whatever this is, 3 times 540, exponent negative 9, so you would get 0.000000162, and then from here, we still need to get D by itself, so you would divide both sides by 6 times 10 to the negative 2, 6 times 10 to the negative 2. So I didn't clear my answer, I left it in there, so I can go divide by 6, exponent negative 2. Hopefully we get the same answer. 4 zeros and then 27. Awesome. So we got to the same point. And again, it didn't ask for us to change the units, so we could leave it as meters. You could convert it to units that make sense, like millimeters or micrometers. It's up to you. Okay, so when you're doing these questions, I encourage you to have this sheet handy. Don't be afraid to use it. You'll get it on your tests and exam. And just work slowly. Be careful. Pay attention to your numbers. And if you have any questions, don't hesitate to email me. All right? Good luck with the daily task.